Perfect. Let me see if I can. Okay, good. Let's just wait one more minute.
Mm-hmm.
Okay, let's start. It's a pleasure to have Jiyuan Ye from NUS. She works, she's a PhD student working with Raza Shokri, who is an expert in this area of membership inference attacks. Currently, uh, if it was Singapore, this would be a very bad time for her. She's not in Singapore. She's in the Bay Area and doing an internship at Apple. And we really appreciate it for you to take the time to give this lecture. So what I'll do is, if there are any questions, I'll relay it back to you. And the floor is all yours. Thank you.
Yeah, thank you so much, So, hi everyone. Today I will talk about membership inference attack, and the slides are heavily based on talks and lectures given by my advisor Raza Shokri. And in this lecture, I will first tell you a little bit about what is membership inference attack, why do we care about it, and then we talk about how people are designing stronger and stronger membership inference attacks. And lastly, if time permits, we will go to see a few examples of what kind of membership inference attack are like successful in various complex application domains, and hopefully it will be interesting to you. So firstly, membership inference attack is related to the topic of data privacy. So let's first look at what existing privacy concerns are already regulated in this GDPR, which is a data protection impact assessment for European Union countries. And I will not go into them one by one, but the idea is that in these regulations, the focus is mostly on data control, data sharing, and access control. So in a sense, they are kind of making an effort to say certain informations are only shared among authorized parties. They do not go into like wrong hands. And to do this, they kind of enforce constraints on data collection, add confidentiality requirement in data sharing, and so on and so forth. What we are going to talk about today is slightly different from this direct privacy risk. By direct, I mean they kind of restrict. Let's imagine a machine learning training setting where a data is trained maybe on the cloud to get a trained model, and then this model is used by subsequent users. So all these regulations really constrain this kind of direct privacy risks that take place in the data collection phase as input for the training, or in the inference phase as input to the prediction API. So they kind of constrain these data are not directly accessed by malicious parties. What we are focusing today is another kind of indirect privacy risk. By indirect, we mean that the user could access either like the weights of the trained model or predictions made by the trained model, which are not directly the training data, the sensitive training data, or like queried data X, but they are kind of a function of the training data or prediction data. And therefore, they also indirectly leak about information for this training, for this data set. What do I mean by that? Let's see a few like real world examples. for this kind of indirect privacy risk. So firstly, this is a kind of the first membership inference attack against machine learning models, where it is shown that for companies that offer this machine learning as a service kind of functionalities, an attacker can tell if a data point is in the training data set of a model trained by these services with 90% success rate. This is done when the attacker only has access to the prediction API. It doesn't have control over what data set is chosen for training or the training algorithm, and can only observe the prediction on like any input data that it can have access to. And this 90% success rate is quite high. It basically says it's possible with very high accuracy to say, I know this is in the training data set or not. Following this, people have also shown that in federated learning setting where the server and the clients communicate with each other about the aggregated model or updated model in the training process, the attacker can observe like multiple snapshots of the models in the federated learning communications, and therefore it is actually stronger than the previous settings where it can only access one final trained model. And in this case, this stronger attacker can even partially reconstruct the sensitive information about the participants' training data. This includes, like, for example, the most basic membership and also sensitive attributes of data in other parties, and sometimes also like demographic properties about the other clients' data, such as are they all from the same demographic group, so on and so forth. And this may not seem very severe, but building on these kind of ideas for inferring membership, people later have designed strong reconstruction attacks where, given a prefix of a data, the adversary can partially reconstruct the sensitive data following this prefix that are used in training. So in this particular example, the prefix is some like address, and then the adversary can basically do reconstruction attack and complete this paragraph with all these sensitive information such as email address, phone number, and this record is indeed in the training data set, validated by searching them on the web, because these large language models are often trained on data from the web, and it can be validated that these reconstructed data are indeed some existing data on the web. And lastly, in the context of another kind of language model where which gives you embedding for like the data that you want, the text that you want, people have also shown that it's possible to identify membership of texts on the training data set of these embedding models. So in this particular setting, they are looking at the clinical birth data set, where each record is kind of a sensitive healthcare scripts, and therefore is very sensitive to individual data, individuals. Yeah. So I hope I have convinced you that until this point that these indirect privacy risks do exist, and they can be quite severe depending on which settings you look at. And all of these tell us models are kind of equivalent to personal data. And therefore, it is very important to understand what are the privacy risks for sharing the model, besides all these existing privacy regulations for controlling data collection and sharing process. And that's the kind of the first message that I want to convey to you today. That is, these inference attacks, they are very useful for quantifying these indirect privacy risk in machine learning systems. So in this talks, in this lecture specifically, we will cover membership inference attack, which asks a very, very simple question that is, given the model, can an adversary infer whether a particular data point is part of its training data set? So it's a question of, is it there or not there? A binary question. And then the success of the attacker give you a metric for the indirect privacy risk of the target model about its training data set. So why do we care about this membership inference attack specifically? Like from first sight, it may seem very benign, because I already know the data that I want to infer membership for, I already know all of its values, then why do I care about whether I know it's used in the training or not? So it turns out that firstly, although these membership information are like this kind of simplest possible information, a binary information, it is useful for recovering more complex information of the data record. So to give an example, let's revisit the text data reconstruction attack example. So here the model is trained to perform a next word prediction task, and it is trained on many texts that may contain sensitive information such as address, phone number, email, so on and so forth. And then how do we use membership inference for reconstruction? The idea is that when you are given a sentence such as this person's social security number is something, you don't know what is this something, and you want to reconstruct that. But you know that it's only possible within certain domains. So for example, here I know that it can only be this specific format of social security number. And what I can do is that, what the adversary can do is that they can basically brute force search over all these possible values for this blank, launch membership inference attack on each of them, and use it to identify the value with the highest probability of being a member of the training data set. And as shown in the before example, this lead to quite successful reconstruction. So this basically shows membership inference is useful as building blocks for more complicated attacks. And secondly, these membership inference attack, although they themselves alone may not be severe enough for people to say this is a privacy violation, very severe privacy violation, it is very useful for kind of measuring how much the privacy loss there are. So it's more used as a quantitative tool in for example, some AI regulations and guidelines to say that I want to be free from this kind of basic attack for privacy protection against these indirect privacy risks. So, okay, so success of adversary for membership inference attack, we have shown that it is a useful tool for measuring the information leakage of models about their training data. But how do we measure the success in an informative way? And what kind of success means it's bad for privacy and vice versa? So now let's see how these membership inference attacks are measured in a standard way to measure the privacy loss. So to measure the success, first you need to define kind of a evaluation setting or this kind of game where that the membership inference attack is performed over. So in this membership inference game, typically there are two worlds. In the first world, the model is trained on a training data set not containing a target data point, while in the second world, the model is trained on a data set containing this record. Then with probability half, the challenger will reveal the model in either the first world or the second world to the adversary. And then it's the adversary's job to say which world does the model come from. So if it can successfully distinguish between these two worlds, it basically means it can infer the membership of the target data X. And if it cannot succeed, it basically means the two worlds are very not distinguishable, or the privacy risk is low. So
Maybe we can pause for just
yeah.
a couple of minutes to see if there are any questions.
Yeah, sure.
Questions?
If we were to think about membership inference attack in terms of differential privacy, can we measure the success? Will it be bound by epsilon in that case?
So the question is, I don't know whether you heard it, that is there, so you can imagine an advantage of the adversary in this MIA game. Is it related, suppose I use differential privacy to train my model. Is there any connection between the advantage of the adversary and the epsilon in the differential privacy?
Yeah, that's a very good question. And we will talk about it later. But the short answer is that yes. And depending on which metric you use for measuring the attacker's success, the translation could be different. And in some metrics, maybe they are like, it's tighter to the bound that differential privacy give on the success is tighter than some other metric. And the advantage is one metric that kind of reflects the attack accuracy. It's kind of the simplest possible metric for attack success. But as we will show, it's not a very, very informative way of measuring success. And we will talk about how to measure success in the next slide.
Okay, great, thank you.
Yeah, and also, actually, I forgot to mention that whether differential privacy gives upper bound for the attack success also depends on what kind of settings we give in this membership inference game. So you can see that in this game, a lot of components can be chosen randomly, such as the training data set, the target data, and also the training random seed. So in some cases, you may want to fix one of them. So for example, if you are interested in what's the privacy loss of my data, which is a very specific data, and I don't really care about what others' data are, I just want to say, suppose they are all randomly chosen, what is the risk of me taking part in the training? And in that case, you kind of fix the data set, the data X, and randomize the training data set, and then you measure the success of the adversary as indication of your privacy loss. In other settings, you want to understand the privacy guarantee of privacy property of a training algorithm. Then in that case, the data are not like constrained. You want to say, what is the overall privacy risk of this training algorithm on all possible input? And in that case, you randomize both the training data set and the target data in this game to evaluate the success as an indication of the privacy loss of that algorithm. And in this animation, we will see a little bit about how this membership inference success can be measured. So here it's a kind of a data domain that is used for training the model. And a small subset of it is like selected for training the model. It's unknown to the adversary. And then suppose we have a membership inference attack that can access this trained model. What it does is it kind of gives you a score that indicates how likely they think, how likely the attacker think when each image is a member of the training data set. And by sorting them out, we can have this whole spectrum of data with different score given by the attacker as being a member. And then to evaluate the success of the attacker, we really need to choose a threshold for saying what data below this threshold I predict member, above this threshold I predict non-member, and then measure the success and failure of the attack. And the question is one threshold enough? So we know that we can choose this threshold in like arbitrary way. We can like move it to the left, move it to the right. And all of these give different attack success measures, right? So to give an informative measure of success, we need to kind of evaluate it for every possible threshold and say for this threshold, we count the number of members predicted correctly versus non-members predicted wrongly. Then we get this true positive rate and false positive rate corresponding to one specific threshold. And then we change the threshold and get another measurement. And we move it forward and backward, and then we get a whole privacy risk profile of this attack strategy. So this is kind of the ideal or like complete measurement of a success of a membership inference attack strategy. And we will talk about it later, how differential privacy could give upper bound for this privacy risk profile. And by looking at this profile, we would know that intuitively, when the profile is closer to the upper left diagonal, it means the member and non-member are more distinguishable from each other under this attack strategy, right? And because here you kind of achieve very, very high true positive rate, which means you predict correctly for member. And you also have very, very low false positive rate, which means you kind of make very little mistake on non-members. And vice, on the contrary, if this profile is closer to the diagonal, it means under this attack strategy, the member and non-member are more or less indistinguishable from each other. So this gives us like a whole spectrum of how much the privacy risks are and what are the good regions, what are the bad regions for privacy. However, it is important to note that an attack strategy only gives a lower bound on the privacy risk of the target machine learning algorithm. That is, if it succeeds, then you know for sure that this algorithm is not privacy preserving. But if it fails, it does not necessarily guarantee that the algorithm is privacy preserving. So we kind of really need to aim for stronger and stronger membership inference attack to have an accurate understanding of the privacy risk. And after this, I will talk about how we should design these stronger and stronger attacks. Before that, if anyone has any questions, I'm happy to answer them.
Any questions? Anybody? Okay, you can keep going. Yeah, Daniel?
Like multimodal models, what sort of data is like more accurate? Is it textual data, image data? Because we've seen lots of examples of text data being leaked, but also image data being leaked. So what is more accurate in these cases?
So the question is, in a multimodal setting, you have data that's text, images, and so on, which are more amenable to model membership inference? Because a lot of the examples you showed were more like text data. What about images or something like that? Is that
Sound too, yeah.
or sound or acoustics or whatever.
I see. So the question is, can membership inference attacks succeed for image or multimodal data?
Yeah, and which modality is probably more susceptible to MIA attacks?
I see. So that's a good question. And in terms of whether they can succeed for other modality of data, for sure, for image data, they can. Like, in fact, this example, both the machine learning as a service example and the federated learning examples contain experiments on image data set. And for multimodal data, it's a relatively newer research question. And there are also like recent works, more recent works that attack multimodal model. And there it's kind of and there it's kind of harder to attack because it's kind of the output there is more complicated. It's not like this classification, simple classification output. And regarding whether they are like more susceptible to membership inference attack compared to other modality, it's still an open question. And it apparently also depends a lot on the training algorithm. And it's not very clear how to compare them in the same basis. And therefore, it's kind of still, it's a good question, but it's kind of an open problem. Yep.
Thanks.
I did have a follow-up question, much along the line of this question. So rather than variation in the kind of data, how about the variation in the kind of model? How do different models perform? Can you comment on how different models hold up to MIA attacks or MIA?
So what the question is that the first question was more about variety of data. Here it's variety of model architecture. What different, how correlated is to different kind of model architectures?
So it's pretty correlated. So basically, one observation people have, which is quite kind of robust as it's tested for multiple papers, is the larger the model is, the more vulnerable it often turns out to be against these inference attacks. And another thing is when choosing the architecture, existing attacks are more successful for like these smooth activations compared to non-smooth activations. So for example, for ReLU activation, it's actually like the performance tend to be lower, and it's hypothesized that it's because different activations have different expressive powers, and maybe when it's smooth, it is more expressive and memorize the data more. But it could also be the case that it's just existing attacks. They are not optimized for certain types of activation function. And things go on again, like for various other factors of architecture. And usually the trend is like the better the performance of the model is, usually the kind of more susceptible it is to membership inference attack, at least for certain points, because it has more capacity to memorize certain points.
Thank you.
All right, so if there are no other questions, let's go into the designing phase of this lecture. And designing powerful membership inference attack is kind of a hot research topic in the last few years. And there are really like a lot of works designing various heuristics for improving it, ranging from signal functions to like different assumptions on the data and training algorithm. But in this lecture, we will focus on one line of work that tries to improve this via reducing the uncertainty of the adversary. And we will see what it means in a second. So in the previous membership inference game, we know that the adversary has many uncertainty over how the training data are sampled and how the random seed are chosen for the algorithm and so on. But these are kind of all these uncertainty that are unrelated to the absence or presence of the target data. And they should be kind of eliminated as much as possible for a powerful attack. That is, the adversary should take these uncertainties into account as much as possible when making the decision, so that it doesn't get fooled by these uncertainty rather than the membership signal. So to be more precise, let's see what these uncertainties mean in terms of probabilities in this equivalent hypothesis testing framework for membership inference. So basically, there are two hypotheses. In one hypothesis, the data are randomly sampled. The population data Z is also randomly sampled, and then the model is trained on these population data. This is the non-member world, because with very high probability, the target data will not be overlapping with the population data. Meanwhile, on the alternative hypothesis, although the dataset D is randomly sampled, the model theta is trained on the dataset combined with the target data X rather than some random population data Z. And in this case, we see what this probability mean, like in terms of the adversary has to consider the fact that the dataset might be randomly chosen, so that when deciding the membership, it doesn't like predict member or non-member just because some factor related to the random sampling process. The good thing about the hypothesis testing formulation is that we know how to solve this binary hypothesis testing problem very well. Namely, the best solution is known as the likelihood ratio test, where we basically compute the probability of observing trained model theta and target data X in the alternative hypothesis versus the probability of observing them in the null hypothesis, which is the non-member world. And if this ratio is large, it basically means these observations are more likely to appear in the member world. And then we basically predict member for the attack. We reject the null hypothesis. And how large should we tolerate the likelihood ratio to be for predicting member is a question that is related to the false positive rate of the attack. If we want some alpha false positive rate, then we should choose the threshold according to that, so that we don't make wrong decisions for like more than alpha% of the non-member models and data records. Okay, so now the question for designing the attack really boils down to how could we compute this likelihood ratio? This joint probability, you can write it down. It's like explicitly expressible in the former hypothesis testing formulation. However, the computing it is actually quite challenging, because you can imagine theta as the model is very high dimensional. And when you want to compute its probability density, it's very hard to estimate it accurately, just because it's very high dimensional. And therefore, what should we do to get over this dimensionality limitation. So what we can do is we do Bayes for the joint distribution, and then observe that when the target data and the population data are both independently randomly sampled from the same population pool, the likelihood, the probability of observing one model is the same in both member and non-member world. And this allows us to cancel out the term related to the probability of theta in this expression and allow us to focus only on the probability of X being in the training data set conditioned on a model theta in the member world versus this conditional probability in the non-member world. And this is a slightly easier problem because the prediction for X is usually like lower dimensional, and you can kind of intuitively interpret it as the likelihood of a data X on models trained with it versus model trained without it. And there are various like tools that one could imagine to use to approximate this likelihood, such as using the loss of X on the model theta or the confidence of prediction using the model theta on the data X, so on and so forth. And there are a vast literature using different techniques to estimate this likelihood. And for now, let's just assume that they are given. So for example, these are the confidence of prediction on X given the model. Then the question really becomes, how can we use it to do a successful membership inference attack? So given target point X and target model theta, how should we determine whether the target is a member or not? So recall that we can compute this P of X given theta in a realistic manner. Then the question is, what should we compare it with to say like, this is a member or not? Of course, we want to compare it with like the alternative world, which is non-member, and then intuitively, if it's more likely, then the non-member world, we say it's member, and if it's less likely, we say it's non-member. So how could we construct this non-member world? So this is a very let's see, a very simple technique that is like brought up by the kind of earliest work on membership inference attack against machine learning model. And there, what they do is that the adversary gather whatever data it can access, which is the population data, and then train a shadow model with the same architecture and using the same training algorithm as the target model, except that it's on the population data rather than the unknown target data set. And then on this shadow model and population data, one can observe what are the patterns of probability of Z given theta for this population data and shadow model. This gives us kind of a comparison baseline to say, what should this P of X given theta be in a non-member world? And then we basically compute how much how much of these population data and shadow model incurs lower P of Z given theta prime compared to the target, which is P of X given theta. So if P of X given theta is larger than a majority of these reference cases, then it basically means it's very likely to be observed on the target model. And therefore it is like a member. And in this example, Z and theta prime basically give you the baseline for non-member world. But is it really that great? Let's look at what it really captures. That is, what is the reason for leakage what is the reason for success for this membership inference attack? So if we look at why it succeeds, we can see that it's actually not that necessary to really train a shadow model. Instead, it suffices to compare the population data with the target data on the given target model. That is,
Maybe do a little bit pause and see if there is, that the idea of using the shadow model is important. Any questions so far? Okay, great. Thanks. I just want to pause so that if they have questions,
yeah.
please go ahead.
Yes. Okay. So, so as we said, what the previous attack is comparing is really how does the target data compare with a population data. Although they train the shadow model, but later people show that it's not really necessary to train the shadow model. Instead, it suffices to use population data because with a large data pool, it's very likely that these population data are not overlapped with the target data. And therefore, they already serve as a good comparison baseline without even training a shadow model. And in this formulation, the attack predicts member if the target data X is significantly more likely to appear on given the model target model theta compared to the population data on the target model theta. And this formulation really allows us to see what contributes to the success of membership inference in this case. So what do I mean by that? It means when we succeed using this attack, it basically means the training data and population data are like very different under the kind of P of X given theta that you computed. And this difference is really just the overfitting probability of the model, because population data, you can see it as data drawn from the same distribution, which is equivalent to test data. And therefore, really, the higher the generalization, the lower the leakage will be as measured by this attack. And it kind of captures only the overfitting reason for information leakage. But this is not really enough, because let's imagine we have an outlier data with very low probability of being predicted correctly by like model, by any model. It's hard to fit. And in that case, because it is hard to fit, it differs. It's kind of although it is when it's in the training, because when it's in the training data set, it's also hard to fit. So when the attack compare it with population data, it will still say that it incurs like significantly lower P of X given theta, and therefore I should predict it as a non-member. So it make mistakes even when these outliers are included, just because comparison with population data is not calibrated for this particular data point. So based on this intuition, there are a line of works that try to be more specific in this comparison and basically train models without this particular point as comparison baseline for the membership decision. So specifically here, the theta prime are trained without the particular point X, and then the P of X given theta prime are compared with the P of X given theta. So this eliminates the cases we discussed earlier, because if X is an outlier point, we will know that both of them are high, high, but the probability will probably be higher when X is in the training data set than not. So it kind of give you the correct comparison baseline for this hard data point X. And to be more precise in this particular attack, the decision is written as if P of X given theta is significantly larger than P of X given theta prime for theta prime being reference models trained without X, then it says it's probably very different from them, so it's a member. And here we are using these reference models to say how likely X is a member. And if we look at the reason for success in this particular attack, we see, like, take the example of very hard training data. Then we can see that the model trained on it versus the model trained not on it, both have like relatively high. Are there any questions?
Any questions?
Okay, yeah, maybe I heard something wrong. Yeah. So basically in this particular example, both models trained on X and model trained not on X have relatively high error, but the model trained on X have slightly lower error. And in this case, this attack will like nicely compare these two when performing the evaluation on the target and correctly predict member and non-member in most of the cases. And for this particular hard example, since these two distributions are very distinguishable, it can reach very high attack performance, close to 1, rather than being like wrong in the previous attack. Okay, so these are the kind of, this attack is kind of one of the most successful attacks currently, but it's kind of also still have its own limitations. So in this slide, let us like dig deeper into what are the limitations of the previous two kind of attacks, one on population data and one on reference models are. So in the first one, we are comparing X target data with population data Z, given the same fixed target model theta. And this attack fails at determining, as we said, it fails at detecting members when P of X given theta is large, regardless of theta, that is, when X is a hard data point. And therefore, in a sense, it's kind of saying this test is not calibrated to what the likelihood ratio is on other models, because it could be large just because of properties due to this specific data rather than its membership signal. Meanwhile, the later reference model-based attack compares theta, which is the target model, with the reference model theta prime for a fixed target data X. And this attack fails at detecting members when P of X given theta is more or less similar to P of X given theta prime. So kind of it's very generalized across different models. And additionally, it may also falsely predict non-members as members if P of X given theta it happens to be larger than P of X given theta prime. This is, why do we say it happens to be? Because here theta prime is the reference model, and usually for computation efficiency, you can only train a few reference model, and therefore it's subject to high experimental randomness. And it, in a way, it's kind of saying, due to the randomness in training the model, the decision could be due to the randomness in the training rather than the true membership. And lastly, this is due to not comparing with population data because that is, the test is not calibrated to what the likelihood ratio is on the population data because it didn't like make explicit use of Z as comparison baseline for its signal. And to reduce the error, since we can only rely on theta prime as baseline, we need to train a lot of theta prime for attacking each target data X. Okay. So how could we design a more robust membership inference attack?
Just
Based on-
1 second. Do you want any questions? So essentially, the basic idea is that there are kind of two large class of methods for MIA. One, where you only look at the model that is being trained. The other one where you also train shadow models and sort of use that in the decision. So these are sort of the pros and cons of both of the sides. I mean, one thing that I just wanted to add is this, where like that Carlini's attack,
Mhm.
you have to build a lot of shadow models. So there is a cost associated with it as well, right?
Yes, yeah. This is kind of the last limitation of this slide. Basically, because it only relies on shadow models or reference models as baseline, so it really need many samples for stable estimation of the baseline.
Yeah, exactly.
Yeah.
Okay, so there is a cost associated with that as well. So because you have to train all these shadow models.
Yeah, because population data is very cheap, but training models is more expensive.
Yes.
Yeah.
Okay, thanks.
Yeah, thank you. And
Yes.
So when you're training shadow models, that implies that you're beginning at the start and training a model alongside it, I'd imagine. Does this functionally work the same for fine tuning, or are you more limited when you're working with models that you don't have access to from the beginning?
Can you repeat that again? So I think basically the way I thought about it is that what happens during, generally now the models are fine-tuned over a foundation model.
Mhm.
How does the story change, basically?
Exactly.
So the idea is that these days, essentially, nobody is building models from scratch. People take foundation models and maybe fine-tune on top of that. Does the story change at all?
so it's kind of the same if you consider the privacy risk for the fine-tuning data, because in that case, you just train the shadow models on top of the same pre-trained model as the target model. And
Yeah, I think that answered the question. So the shadow model would be all the fine-tuned models on top of the foundation model. Okay, great. Thank you.
okay, yeah. Okay, so observing all these limitations, we want to introduce one last attack that is like stronger than both of them and more calibrated, so we'd say it's more robust. So what do we mean by it? It's basically saying the attack should be calibrated to what the likelihood ratio is on both the reference models and also on population data. So kind of take these two sources of information together to make the attack decision more robust. And additionally, because we often need to identify member in a huge population pool, for realistic computation cost in that setting, the attack should be offline. That is, it shouldn't require training new models, shadow model or reference models for attacking each data point. What do I mean by that? In previous examples, the reference models are trained without X for each X you want to attack. And here in this attack, we want to train the same reference model for attacking each X. So what do we mean by the first point, which is calibrate to both reference model and population data? So we basically observed that previously, we only kind of cared about either one of the green arrows. That is, we are either comparing X and Z given the same target model theta, or we are comparing like theta and theta prime given the same target data X. Meanwhile, if we compare, like use another layer of comparison between the two green arrows, we can kind of aggregate these two information source of reference model and population data together simultaneously. So what this attack does intuitively is that it asks this counterfactual question of what if the model is trained on Z rather than X? How would the P of X given theta compare to P of X given theta prime? So instead of only relying on like the comparison between target data and population data, or the comparison between target model and reference model, we do two layers of comparison here. So more precisely, the attack kind of computes how likely are X given theta compared to Z given theta over how X and Z compare with each other on reference models. So the first layer of comparison comes from X and Z, while the second layer of comparison comes from the population probability of Z and X, which uses the reference model to estimate. And importantly, the reference model here are trained just on population data. They are not excluding one particular data point, so it's fully offline and does not need new models for each X. And as this attack incorporates the population data into its decision, it turns out to be significantly more robust than existing reference model attacks when only one offline reference models are given. So intuitively, this is because when you only use one reference model to aid your attack decision, the randomness in training is too high, such that you kind of tend to make error due to insufficient number of reference model. Meanwhile, if you incorporate population data together with reference model, you can significantly reduce the estimation variance or error. So here, RMIA is the last attack, which incorporates both population data and reference model, while the other two attacks, attack R and LIRA, are both reference model based attacks that do not explicitly use population data as decision baseline. And additionally, the attack really shines when we want robust performance over like out of distribution data. So this is often the case in like in deploying this attack, because you don't know like what is the distribution of the training data. So it's very likely that you will need to perform the attack on many possible data which could be out of distribution to rule out points that are non-member. And in this case, because of the comparison with population data, this attack is significantly more powerful than all the previous attacks that only use reference model. Because out of distribution detection is essentially a problem about how different two data population are, and reference model alone cannot capture that information very well. Okay, so with that, I would end the kind of section about designing the attack, and as conclusion, there are various attacks which have different strengths, and it is important to use the strongest attack when evaluating the privacy risk. And in this open source tool of Privacy Meter, people in our lab are building like these baseline implementations for these various attacks under different settings, so that practitioners or like curious researchers can really easily see how they perform in their interested settings. and see which attack performs the best. And we also try to be, we try to include all possible attack and especially the best known attack. And you can check it out. And it's you can check it out for all the various attacks and how they perform. And
One question on this this GitHub repo: does it also include MIA attacks on foundation models, or this is kind of a pre-foundation model attacks? So there are membership inference attacks also on foundation models and fine-tuned models. Does this include that, or it's orthogonal to that in some sense?
So in terms of examples, I believe there is one example there about causal language models.
Mm-hmm.
And in terms of like the APIs, we are kind of trying to, so the tool is built with freedom of the user to choose various models they like. We kind of take the model as an input. And of course, these models can be fine-tuned on foundation models if the user like. So it's kind of a part where the user has freedom to choose. And we are focusing on designing the attack algorithm. Yeah.
Okay. Thank you.
Yes. Okay. And now we still have around 10 minutes. And if there are no other questions, I will quickly go through some of the examples of membership inference attack in various domains. And some of them are quite interesting and have serious implications for example, reconstruction. So if anyone has any questions, feel free to say it now.
Questions? Okay, please go ahead. Very eager to see the examples.
Yeah, so as the first example, this is a paper that is performed on models trained on speaker annotated TED Talks. Of course, it's not a sensitive data set, but it's kind of just illustrating how membership inference is possible in this generative model setting. And in this case, the number of sentences known from the author really matters. And as it increases, the attack becomes more and more successful because it can use like all these sentences for making the attack decision. And what's more interesting is that in this paper, the authors also offer various examples of what data are more vulnerable in the sense that it's identified as member correctly more often. And this is something that we believe that various papers should also do later. And it gives you insights of what are the records look like, or what do the records with high vulnerability look like. And in the context of masked language model, where the goal is to train an embedding, people have also shown that by doing these more calibrated membership inference attack, rather than like the baseline here, which is the kind of like shadow model attack or population attack, you can get extremely high privacy risks at the low false positive rate region. That is, for a small amount of data, the attack success could be very high. And the membership patterns are also like very, very distinguishable for some data points. And the experiments are done on clinical bird, which is kind of a sanitized version of a medical data set where medical records are supposed to be sensitive, but due to the anonymization, it probably isn't so serious, but it's just illustrating the possibility of doing membership inference attack in these settings. And this is another example for image classification. It's on the C5100 dataset. And again, it's not really that kind of vulnerable dataset, but it's illustrating that the attack succeeds also in this kind of image domain. And also, as we see, usually the larger the capacity of the model is, and the better the performance of the model is, the privacy will go down. This is intuitive because these models have higher capacity to memorize each individual training data. And for federated learning setting, the adversary has the freedom to exploit the aggregate parameters and updated parameters across multiple communication rounds. And to this end, an interesting observation is that when the membership inference attack performance indeed goes up when the adversary observes multiple snapshots of the trained model. And interestingly, when it observes the later phases of the training, the attack accuracy is better than when it observes earlier kind of epochs of the training. And the idea of how this attack is done is the attacker, which is one malicious party for the federated learning setting, they kind of increase loss on a particular data point that it wants to infer membership for. And then ideally, another participants correct it back only if this X is part of its training data. So the adversary can do membership inference by seeing whether this X is corrected back in later updates of the model. And this threat also exists even when the adversary only observes one final trained model and not any snapshots. This is usually like assuming we are doing some kind of secure multi-party computation in the learning process so that each client, although they update the model, send the model, get aggregated model, they do not see the snapshots of the model in inner communications, but only see the final trained model. And even in this case, the attacker can do some kind of similar to poisoning attack strategies to increase the vulnerability of other participants' data. And this is quite severe because this is assuming the adversary only has one final trained model, and it's very realistic in terms of the threat model that are commonly, it's kind of the strongest settings ensured by these secure multi-party computation protocols. And here is a plot that illustrates how much the privacy loss would increase when the adversary has the ability to poison their data set. So by that, the blue line means the adversary use like clean samples and try to infer membership of data in other participants' data set, while the orange line means the adversary can maliciously poison its data so as to increase the memorization of other parties' data. And finally, I want to show you a way of a consequence of this membership leakage. So here, this is one slide, basically captures this membership leakage in an analytical way. So what we mean by membership leakage is basically how distinguishable the trained model's predictions are on a query queue when one training data is different from the training data set. That is, we remove this data out, known as leave1 out setting. And higher distinguishability in this leave1 out setting means higher membership leakage. I wouldn't expect you to like know all these symbols at once, but intuitively, it basically says it basically is formulating the membership leakage as leave1 out distinguishability. And what can we do under this formulation is that we can show that this vulnerability can be exploited by an attacker to reconstruct training data. That is, in a Li-1 out setting, this statistical distinguishability is maximized when querying the model at the differing data itself. And consequently, if the adversary has access to how the model prediction looks like in this Li-1 out world, it can maximize it to allow precise reconstruction of the training data. That is, when it starts from randomly initialized data point, it can move it along the direction that increases the membership leakage and move it again to further increase the membership leakage, so on and so forth, until it ultimately kind of recovers what are the differing data in this Li-1 out setting. This is aligned with like the previous example of how membership inference attack allows reconstruction for the text data, and basically shows that the prediction membership leakage allows reconstruction even from this randomly initialized image, not even constrained data domain. All right, so that is the end of the talk. And to end, as a conclusion in this talk, we talked about what are the best known attack strategy for membership inference and how to evaluate it as an indication of privacy loss. And I want to mention here that there are also guarantees, which are upper bounds for the privacy loss given by, for example, epsilon delta differential privacy, plotted as red lines in this plot. And the challenge for accurate privacy loss understanding is really to like minimize the gap between these two. And in this talk, we talked about designing better attacks, which pushes for the lower bound. And there are also many other challenges in improving the upper bound and also resolving other tensions between privacy and different other properties of the training, such as fairness and so on. Yeah, so that is the end of the talk. Thank you.
It was a great talk, Jiyuan. Everybody, thank you. And any questions, last questions? We have a couple of 1 or 2 minutes left. Okay, that was a great talk. Thank you so much. You have, yeah, there's one question.
Yeah, so arguably LLMs nowadays are pretty accurate with predicting the next word and all that. I was curious to know I was curious to hear your comments on what approaches that these LLMs currently use to prevent MIA. If
I think I can answer that. They don't do anything. So I think what the question was, do the new models do anything to alleviate membership inference attacks? And I think the answer is no. Right? Is that true? They're not doing anything with DP or anything to alleviate these attacks at all.
So meaning the pruning happens on the data set, like the data engineers themselves?
I think they're just worried about giving you the best answer and not worrying about privacy. Utility always comes first. The dollars comes because of that, not because of privacy. So, right? I mean, would you say that they're not doing anything about membership inference attacks or privacy things at all right now?
Yeah, and it's also because for these language models, usually the data set you have are pretty large. For example, for pre-training, they are like very, very large scale. So it's actually existing membership inference attack are not too successful on that. And in terms of fine-tuning, I guess it's just they assume that the fine-tuned model is not like released or something.
Yeah.
So yeah.
Okay, thank you again. Thanks so much. I upload generally on YouTube, so I will share the recording with you.
Okay, yeah. Thank you so much.
No problem.